The question we are solving now belongs to test series 5. It is of control system subject. In specific, it belongs to compensators and controllers. As per the question, there is a control system which is closed loop. As shown in the figure, the control system has a PID controller with parameters as Kp, Ti and Td, and the forward path transfer function which is connected in cascade with the PID controller is 1 by s multiplied by s plus 2 multiplied by s plus 4, and please note that the feedback here is unity negative feedback. So here, as per the question, we need to find the optimum setting for the PID controller, that is the parameters Kp, Ti and Td using Ziegler-Nichols method. Here we need to find the optimum setting of the PID controller parameters using Ziegler-Nichols method. We know that in case of Ziegler-Nichols method, the derivation of the parameters Kp, Ti and Td is dependent on the critical gain and critical time period. Now first let us find out critical gain and critical time period. Based on these two quantities, we can find out the optimal setting for the PID controller. We know that the critical gain is given by the value of K for marginal stability. So, so by so from this we can write the characteristic equation of the system as 1 plus g of s multiplied by h of s is equal to 0. Please note that when we do this, we have to assume that the PID controller is replaced by a proportional controller of gain K. So from this we see that the characteristic equation can be simplified as s cube plus 6x square plus 8s plus k is equal to 0. Now, upon doing the Routh-Hurwitz analysis, we see that the entries in the first two rows are given as 1, 8, 6 and k. Now let us find these two entries. We see that the entry here can be obtained as 6 multiplied by 8 minus k multiplied by 1 divided by 6, that is 48 minus k divided by 6, and this quantity is k. And we see that for marginal stability, k should be equal to 48, and this is considered as critical gain. Now, the auxiliary polynomial can be written for k is equal to 48 as 6x square plus 48 is equal to 0, and upon substituting s is equal to j omega, this can be simplified as omega square minus 8 is equal to 0. So upon simplification, we see that corresponding critical frequency omega c can be written as 2 root 2 radians per second. So from this, the critical time period Tc is equal to 2 pi by omega c, which upon simplification boils down to 2.24 second. From this, we see that upon assuming that there is only a proportional controller of gain k, we got the critical gain as 48 and critical time period as 2.24 second. Now let us find the parameters Kp, Ti and Td using these two quantities, that is Kc and Tc. Kp can be written as 0.6 times Kc, which is boils down to 28.8. Ti can be written as Tc by 2, which can be simplified as 1.12 second. Td can be written as Tc by 8, which can be simplified as 0.285 second. We see that the values of Kp, Ti and Td that we got here is the optimal setting of the PID controller using Ziegler-Nichols method. Hence, the correct option representing the optimal setting is D.